In this video, we are going to talk about the normal distribution. So this is going to be the last section that deals with distribution functions. So far we've talked about the binomial distribution, and we said that that was a discrete random variable distribution, and we were able to use the binomial CDF and the binomial PDF function on the calculator to try to figure out the probabilities of certain things occurring when there was two outcomes. Now, this normal distribution is things that we've seen already in our stats course. So let me just remind you a couple things about the normal distribution. So we know that in the middle, right in the middle of the distribution, we have mu, okay, which is basically our mean of our distribution. And then we also have sigma, which is basically our standard deviation. And remember that these were for population. Okay, so this was the population standard deviation. So every single possible person, or I don't know what I'm modeling, animal, whatever, is all of the data. And when I plot it, it looks like a normal graph. So basically, remember that it is bell-shaped. Okay, so it looks like a bell-shaped curve. It is symmetric, so basically I can fold it in half. If I fold it in half in the middle, you can see that it has some sort of symmetry. Also, something else about this is that it has a known mean and standard deviation. Okay, so we know what those guys are, and this is in terms of the population. Okay, so basically, whenever you see a problem, these two numbers, the sigma and the mu, are always going to be given to you. Okay, now that's not really necessarily true, and we've done enough stats to know that it is not possible for me to get every single possible person in San Diego, for example. There's no way. And then also something else that we know about continuous distributions is that the area is equal to 1, okay, or 100%. So basically, if I were to shade, if I wanted to find all of the area under this particular curve, all of this will equal to 1 because it is a probability distribution, and we did that with continuous random variables. So I guess one more thing to kind of note about the normal distribution is that this is a continuous distribution. Okay. So as opposed to discrete. So now usually we're gonna have a couple of terminology and also notation mainly. So here's a couple of notation things. So we already know mu. Mu is gonna be the population mean. Okay, we already know what sigma is. Sigma is gonna be the population standard deviation. Okay, and then we're going to have a value of x. X here is going to be an observed value. Okay, now usually what we want to say, so x is some sort of observed value. So for example, if I were to look at all the possible heights, so let's say the mean height was, I don't know, 59 inches. Okay, so here's the mean. So all possible heights, you can see that a lot of the data is going to be within close to 59 inches. So what this x value is going to say is that, okay, let's say, well, not everyone is 59 inches. Maybe someone is 55 inches. Well, what we want to be able to figure out is what is going to be the probability of this person being less than 55 inches. And what we really have to do is be able to figure out this area under this curve. And what we found was that finding the area of the curve, well, one way that we can do it is to try to figure out some sort of shape that we can try to figure out this area. Notice that this doesn't look like a triangle or some sort of circle. It kind of curves a little bit. So we can't quite use any of the known shapes, any of the formulas for the known shapes for using geometry. So we have to use something else. So I'll show you what it is. But that's basically what we're going to try to do, find areas under the normal curve based on some given information. Now here is some notation that I like to use, and I want you to use it as well. And this fancy notation that looks like this. So this is a notation that I would like to use. So this is basically what this means. So translation into English. This means x follows the normal curve with mean, mu, and standard deviation, sigma. So that's what this means. So x, that's just x, follows, that starts for that, the normal curve, which is this guy, with mean, okay, so the mean part with mean goes basically here, and standard deviation goes in there, okay? So that's basically what all this means. Now, sometimes follows can be broken down to is distributed, okay? So you can say x is distributed normally with the mean mu and standard deviation sigma. So that's basically what this guy means. And I want you guys to be able to be very familiar with this and be able to write it over and over again. So this is really important. I really want to make sure that you guys write this notation, okay? So x is normally distributed with the mean mu and standard deviation sigma, okay? So you can say the data is normal with a mean mu, standard deviation sigma, okay? Now, something to do before we start doing some of these problems that deal with something like this, I want to recap something that we've done before, which is z-scores. Okay, so we talked about z-scores before, and basically z-scores, we had a formula which was just x minus mu divided by sigma. Okay, so basically what this says is, remember that z-scores were how many standard deviations you are from the mean. Okay, so that's basically what that was. So z-scores were just how many standard deviations you are away from the mean. And actually what we said was that the z-scores, all the good values for z-scores were between -2 and 2. So all good values. Okay, and anything that was outside of -2, anything that was less than -2, and anything that was greater than +2 were all bad values, so they were unusual. And we're actually going to prove to ourselves why that is the case. In other classes, it might be -3 or 3, but in our class, it would be -2 to 2. Okay, so we had that, let me just go ahead and write it down, recall that a z-score greater than 2 or less than -2 is considered unusual. Okay, so that's what we kind of said, and what we want to figure out is why was that the case. So before we kind of just took it as a given, but we want to know why that really is. So something to note about z-scores is that all z-scores are normally distributed with a mean of 0 and a sigma, a standard deviation of 1. Okay, so this is something to kind of note. Okay. All right, and basically you can kind of think about it like I'm moving this x value mu units, so I'm kind of standardizing it and making it into a nice shape. So this just go ahead and just take it as a given. This is always, these scores are going to be with the mean mu and the standard deviation sigma. Okay, to prove it, it's a little bit mathematical. You kind of have to think about shifting and compressing of curves, and let's not get into that. Let's just go ahead and take it as is. So what are we going to do? Okay, so we know this fact that all z-scores have a mean of mu equals 0 and standard deviation of 1. Okay, so why is that the case? So basically what this is looking like, and if I look at the normal curve, you have 0 there. And remember that we were 1 standard deviation. Well, that's just 1 and 1. Move 1 down, 1 over, and then if we keep adding 1 and 1, you can kind of see in the curve that the further down I go, the less area you're going to have. So what we're going to try to figure out is that what is going to be this probability. Okay, I want to figure out what these probabilities are, okay, to really prove to ourselves that these are unusual. Okay, so what we're going to be using is something called Normalcdf. Let me write it a little bit downward. So we're going to be using another function in our calculator that's called Normalcdf. And what Normalcdf has, it has a lower bound It has an upper bound. It has a mean, and it has a standard deviation. Okay, so that's basically what normal CDF is. We're only going to be using this, normal CDF. Now you might be wondering, okay, what is going to be normal CDF? Well, if you go to your, back to Canvas, so here's Canvas, and if you click on the module section and go to finding normal probabilities, the steps, so let's go ahead and click on that, and let's try to download it. Download. So you'll be able to see here the steps. So if you have the TI-84, like a graphing calculator, these are the steps. Okay, I say what the steps are. I even give a couple of examples. So you want to kind of take a look at these. Normal CDF. We're not going to be using normal PDF, so this one's going to be done. We're only going to be using these two, normal CDF and inverse normal, and we'll talk about inverse normal, what that means in a little bit. So here are the steps if you have the graphing calculator. Okay, and I give you a really good example of what you should be doing. So and if you have the TI-36X Pro, here is the directions as well. So if you have this calculator, let me show you. So you have that calculator. These are the directions. Okay. All right. So now let's go back. So let me show you how we're gonna do this. So let's say we wanted to figure out this probability. Okay. So find the probability of x being less than or equal to -2. Okay, so let's try to figure that guy out. Okay, oh, not x, z. Okay, so that our z-score is less than or equal to -2. Okay, so what you always want to do with these types of problems, you always want to draw a picture. Okay. And the reason why a lot of students tend to get this wrong is because they don't draw a picture. Okay, so always draw a picture. So a picture of what? So we're always going to draw a picture of the normal curve, because we know that z-scores are normal with a mean of 0 and a sigma of 1. Okay, so that means 0 is going to be right here, right in the middle. That is the mean. Okay, and what are we looking for? Here's -2. -2 is right below 0. And what do we want? We want everything that's less than -2. So everything that's less than -2 is going to be all of this area. Okay, so now what I want you guys to kind of think about is that this area is going to keep going until it goes to -infinity. So it's going to go all the way down to, you get a really, really big negative number. So it's -infinity. Okay. All right, and over here, if you were looking at the other side, this will be positive infinity. So if you really need, I think it would be smart to kind of label these -infinity and positive infinity. Okay, so now what we want to do is we want to find the area under this curve. So in order to find the area, all you got to do is just do the normal CDF function. So we're going to do normal CDF. And now what we're going to put something in our lower bound. So our lower bound, okay, so what would be our lower bound? So our lower bound is basically the lowest point in this particular area. Notice that in this particular area, our lowest point is going to be -infinity. Okay, -infinity. So this guy is going to be -infinity. Okay, that's going to be our lower bound. Okay, now how are you going to put -infinity in a calculator? Well, one thing that you can do is you can put -1 with a whole bunch of zeros afterwards. So you can either, so this is what you would want to put. And you'll see that sometimes your calculator is programmed as well. Now my upper bound is going to be, where does the area end? So our area is going to end here. Okay, what is it? -2. Okay, so that's my upper bound. Then after that, it's going to be my mean. My mean in this case is going to be equal to 0, because that's what that equals to. Okay, and then what's going to be my standard deviation? Well, my standard deviation is going to be equal to this guy, which is going to be equal to 1. Okay. All right, now all I have to do is put this in our calculator. Okay, so let me go ahead and go to the TI-36X Pro first. So what you want to do, make sure that you have your directions with you. What you're going to do is you're going to first press second data. Oh, and maybe turn on my calculator first. Second data. Okay, then what you're going to do, you're going to go down up over to distributions. which is where we found our binomial. If you keep scrolling down, binomial was right there. But instead what we're going to do, we're going to click on number 2, which is Normalcdf, and we're going to press enter. Okay, then it's going to ask for the mean and the sigma. Okay, so our mean, remember, was 0. Our sigma was going to be equal to 1. So that's going to stay there. Okay, so do nothing. Okay, then our lower bound. Our lower bound, notice that they're already there. These numbers is basically negative infinity, negative 1e99. That just means negative infinity. Our upper bound is going to be positive infinity. Okay, so our lower bound was negative infinity because that's what we said, and our upper bound was going to be equal to negative 2. So we're going to write this negative. This negative is right down here, down to the decimal point, negative 2, and then we're going to press enter, and what we're going to get is 0.023. Okay, so my probability of this is going to be 0.023. That is going to be the probability of z being less than or equal to negative 2. That's what that is. Okay? All right, now let's find this probability. Find the probability of z being greater than or equal to 2. Okay, so what would that be? Well, what you want to do is you want to draw a normal curve. Okay, remember that z is normally distributed with a mean of 0 and a sigma of 1. So my mean is going to be at 0. 2 is going to be over here. Okay, and then we're looking for everything that's greater than 2, greater than or equal to, so it's going to be all of this guy. Okay. All right, so now what is going to be my lower bound? Let's just write it like this. My lower bound is going to be equal to 2, okay? Because notice that my area starts at 2, so that's the lowest end of the area. That's going to be at 2. What's going to be my upper bound? Well, my upper bound is going to, notice that the area keeps increasing all the way to positive infinity. So my upper bound is going to be positive infinity. My mean, mu, is going to be equal to 0. And my sigma is going to be equal to 1. So the probability of z being greater than or equal to 2 is going to be equal to, all we got to do is put in this information into my calculator. Okay, so let's go back to my calculator. Let's press second quit. We're going to put second data again. Go over to distributions. Go down to Normalcdf. Our mean is still 0. Our sigma is still 1. And then the lower bound is going to be now 2. And my upper bound is going to stay at positive infinity. So that one stays the same. That's positive infinity. Okay, then we're going to go down to calculate, and we're going to get still the same thing, 0.023. So what this means is that this area right here that we shaded is equal to 0.023. And actually, this should not be, why these probabilities are the same should not really be any... you shouldn't be surprised, because remember that normal curves are symmetric. So basically the area over on this side is going to be equal to the area over on that side. Okay,